All right, well, this is the second talk in this conference on symmetry so far, or maybe even more, depending on how broadly you define symmetry. And so first, I'll just go through a little bit of the motivation for why we started considering symmetry measures. And in the history of physics, symmetry has been a pretty good bet. The classical Noether's theorem is considered one of the sort of most important results, and one that is still used very much today. If you're in a modern physics program, you will probably end up seeing this quite a lot, depending on which area you study. And so this is the basic idea that you have some symmetries of a classical system, continuous Lie group symmetries, and these symmetries, each of these symmetries has a corresponding conservation law with a corresponding conserved quantity. So for example, the symmetry under changes in the reference frame in classical mechanics correspond directly to conservation of momenta and energy. Now, in quantum mechanics, this actually, if anything, becomes clearer. We have observables, or we have that generate unitary transformations. And the relationship between the unitary transformation and the generator, in fact, one of its properties is that the generator ends up looking like a Noether charge of the observable. And so these are what lead to what we call good quantum numbers in sort of a basic quantum physics class. These are the things that commute with the Hamiltonian or commute with the time translation, and therefore they don't change with time. And these are the quantities in which, if you're trying to prepare a state, you would generally want to prepare. So what this leads to, of course, is the question of, well, let's say we leave the idealized classical world or the pure state quantum world and go into the noisy world that we all live in, where systems are open, there is mixture, and the question becomes, well, what can we do with symmetry here? And so traditionally, people often talk of quantum channels in analogy to the classical channels from information theory, which are often thought of as telecommunication systems. Though in generality, these are really a very general description of open systems that may contain both classical and quantum components. So I think the Steinspring dilation actually provides a fairly good intuition for this, because one way that you can think of a quantum channel is that you're observing a subsystem, which is your quantum state, and you're observing it, but what it's doing is happening in the context of a larger environment. And this environment is time evolving. And since you don't observe that environment, you trace it out, and you're left with a quantum channel. So specifically, we may take a Hilbert space A, define on this Hilbert space a set of density operators, which are live in the Schatten one-normed class, and of course a unitary group of transformations on A. Now we can take an algebra G, usually a group, though one can also do this with quantum groups and other structures in theory, and we'll call this the symmetry algebra, or the symmetry group, and we will define a representation of this group on these unitaries that, of course, act on the quantum states and then the densities. And if a certain quantum channel that maps densities to densities in this space is a completely positive trace-preserving map that also, in some sense, commutes with the representation of this group, then we will call that a G covariant channel. And so this is what's going to define symmetric evolutions for us. So this leads to, so once we can start defining things concretely, we can think about why else we might start to study these. And one of these examples that is presented in the thesis of Ayman Marvian from Waterloo, he works with Rob Spekkens, or he worked with Rob Spekkens there, is that these are a pretty good description of issues with reference frame. So he gives an example in which Alice is one party in a quantum experiment, and Bob is another party. Alice is presumably on Earth with access to very good preparation and measurement equipment. But Bob is in a satellite somewhere with some restrictions on what he has access to, and his coordinate system might not be precisely aligned. And by the principle of relativity, if his coordinate system is off in a way that he cannot measure or predict, then this is relative to Alice, to states prepared by Alice that she's sending up there, actually equivalent to perturbing the state. And so we can express that as a quantum channel. And this quantum channel is a weighted average of representation of elements of the representation of the symmetry group. And so if it so happens that this average is uniform or is Haar-weighted, then we actually get what's called a conditional expectation, which I'll go into more later. And so this is sort of saying how much symmetry can you preserve in a system that maybe has one of these imperfect reference frames or possibly is directly hitting the state with these transformations. And so we measure this by defining monotones. And from the quantum information context, you may recognize this as having the appearance of something like a data processing equality. Really, we're looking for maps from the states to the real numbers that are non-increasing under covariant channels. And there are several ways to construct these, but one example that we'll be using a lot is this Holevo asymmetry measure. And with respect to a group, this is saying how much more entropy does the state have after you've averaged over the actions of the group. And so you can imagine that a state that is already very symmetric, this group averaging won't do very much to it. And so you'll get a very low asymmetry. If it's fully symmetric, then this becomes 0. And if the state is highly asymmetric, then of course this is high. And now, again, this actually in its definition uses the conditional expectation. So with asymmetry monotones defined, we have the ability to construct a resource theory. And so we can compare this to the situation with entanglement, in which we have some quantity that is we measure by monotones or define by monotones. We have some free operations. In the case of symmetry, these are the covariant channels. In the case of entanglement, these would be LOCC operations. And we have a set of free states, states that should, ideally for a faithful monotone, have value 0. And so these are the symmetric states in the symmetry case, which are analogous to the separable states for entanglement. And this has a bunch more applications. Quantum orienteering is actually when using quantum states to communicate a direction in space. Of course, this is very directly related to the symmetry with regard to spatial rotations. In that regard, you can also use a quantum state to fix a reference frame. Spekkens has a lot to say about this being a way to quantify measurement capabilities. And then coherence can also be defined as a resource, which is a symmetry with respect to a certain dephasing. So this is an entropic asymmetry measure, and one aspect of entropies that we'll be using a lot is that we can write them in terms of norms. So you've probably seen the Rényi entropy in this form before. We also have this sandwich conditional Rényi entropy, which is a generalization of the conditional entropy. For p equals 1, this is this sort of conventional conditional von Neumann or Shannon entropy. These are defined with respect to Schatten norms. And this is what allows us to start to bring in some of the operator algebra structure. And so what we want to do is to generalize these Schatten classes. Instead, think of these in terms of dual spaces and von Neumann algebras. And so this is a slide that I probably won't need to spend much time on with this audience. We are looking at tracial von Neumann algebras and trying to think of what we can do with these. And so since it has a trace, we can define a norm that is essentially analogous to the Schatten norm. And then there are these augmented LP spaces, which are putting three things together. The norm is defined as sort of the minimum over the ways to construct this product. And these, they of course have L, Q, and R, which are, they have more parameters controlling what the different norms are here. These are interpolation spaces. And so this basically means that we have sort of two hopefully easy to characterize instances of these spaces, and we can start to look at norms that fall in between those and bound them by this interpolation property. Now, the duals to these are conditional LP spaces. What's interesting about these is that so where we have the trace and the von Neumann algebras, these actually have a conditional expectation. So again, that's, you see that coming up. And of course, we can define a norm for these, but the thing we care about most is that these are, again, interpolation spaces, and that allows us to prove all sorts of useful properties. Now, what does this have to do with asymmetry? Well, this Rényi conditional entropy has a norm expression in terms of Schatten classes, but we can also find that this is in fact equal to this augmented LP space norm. And so this gives us the entropy in terms of the LP space norm. And what this means is that the interpolation property will be useful in understanding entropies. It also, because of these conditional LP spaces, will allow us to relate some things to conditional expectations. And so what we do with this is we actually decided to generalize or define a generalized asymmetry measure in analogy to the sandwich conditional Rényi entropy. This, I won't go through the proof here, but we did prove that this is an asymmetry measure. It satisfies this data processing inequality. And so,
sorry, n is always the fixed points of the group, or what is this? How is this related to the group?
So I'll get to that in the next slide, actually. Maybe that's a...
I thought I missed that.
Yeah, so we want to look, so this is defined with respect to a certain subalgebra. But we'd like to see, okay, how does this relate to the group algebra? And it turns out in the case where p equals 1, it's equal to the Holevo asymmetry measure for a group, where the group is the representations of the commutant of the algebra to which we've taken this asymmetry measure. And so there's a slight sort of, I don't know, switch here, because with this, we're writing it in terms of the group that we're sort of removing or averaging out. But over here, we write this with respect to the subalgebra that we're keeping inside of the larger algebra M. And so often, if we're using the 1, I'll drop the 1 for notational convenience. So this was sort of interesting to us, but we wanted to look for more ways we can use this. And so what we realized was that this was actually related to this quantum capacity. And so just briefly, the quantum capacity, you have two parties, Alice and Bob. Alice is sending qubits to Bob. Sort of in this average sense, how many can she transmit without any feedback or assistance? Those change things. And this has an expression as the regularization of entropy formula. As some have pointed out, this actually makes this quite nasty. In many cases, we cannot explicitly compute this, but we can at least say that it's related to a certain entropic quantity. And it turns out that it also can be rewritten in terms of this Holevo asymmetry measure. Where here, I'm actually using, rather than the algebras, I'm sort of writing mu AVB. What is that? Well, we can define an algebra that is essentially the operators on B, an algebra that is the operators on AB, and we're going to trace down to one of these. And so this is also a fairly quick way to see that the Holevo asymmetry, or at least the maximum over states, must be superadditive. Because we know that quantum capacity is superadditive. That's why this formula has an infinite limit and causes us so much trouble. So we also had some ways to estimate quantum capacity, which we sort of were able to port to this asymmetry measure. And so we're going to build up a particular form of channel here. So V goes from A to B cross E as an asymmetry. We have this channel VA. V is acting kind of like a Stein spring isometry, but we put this extra A in, which is going to weight some of the Krauss operators in a variable way. And then, so now we have a couple of subalgebras. N is generated by the Krauss operators themselves, and so that lives in B. And K and L both live in E, K being this sort of, so this is a complementary channel, which is what you get if you take the Stein spring dilation, but instead of tracing out the environment, you trace the output. So this is everything that the output didn't get. And then L is another algebra in the environment, and we're going to impose this condition that there's a certain independence. And so the trace of an element in L and an element in K is a product of traces, or a product of normalized trace with sort of more, I don't know, unnormalized trace, at least in finite dimensional systems. And so this, for this class of channels, will allow us to estimate the output asymmetry as compared to when A is 1. And what is A equals 1? That is actually another conditional expectation. And so there's a lot more details to this, which you can read about the full quantum capacity version in one of our previous papers, which is currently on the archive on TRO channels. So we can do this for yet more things. Classical capacities tend to look like mutual informations, and so we can rewrite those using asymmetries. This minimal output entropy is also a quantity which has been considered and has played some importance in the theory of quantum communication. And so the question then is, well, why does this work? Is everything asymmetry? Well, the reason why it works is really that this conditional entropy is a special case of taking a conditional expectation. We're essentially tracing over the algebra of one of the subsystems. And that's how we trace out a system. A trace is a kind of conditional expectation. So really what it means is that this Holevo asymmetry measure is something very general. It's a generalization of a conditional entropy. So what we're doing is we're replacing a partial trace by a conditional expectation. Instead of looking at the density matrix picture, we're looking at a particular class of von Neumann algebras. And we are generalizing from physically separate subsystems to something we call commuting squares. And so before I go too much into that, just sort of an example. So here are two sort of extreme cases of this. One is the one that I've been mentioning, where you essentially have your conditional expectation onto an algebra that are the transformations of a subsystem, and so you're tracing out a different subsystem. This equality, you have to be careful with this. You do end up with extra log dimension terms, because if you trace out, usually you simply get rid of that subsystem. But if you take the conditional expectation, then that subsystem is still around with a completely mixed state in it. And so you have to remember to keep track of that when you're adding up entropies. But otherwise, this is basically what we're doing. And so the sort of opposite extreme from this is where the variables are complementary. So we can take the canonical position and momentum variables, and one of the conditional expectations is essentially a completely dephasing channel in the X basis. So these are both examples of what we call a commuting square. We have a von Neumann algebra M. We have two subalgebras L and N. There's a conditional expectation onto each of them. And what makes this a commuting square is that we can take the two conditional expectations. They essentially commute with each other. Taking both of them together is equivalent to some other conditional expectation. In some cases, this basically gets you down to the scalars. You get rid of everything. In other cases, sometimes you may leave something non-trivial here. And so in the channel picture, which I won't go too much into right now, these channels, there's some basis in which conditional expectation channels look block diagonal. So what do we do with this? Well, using this asymmetry idea and the properties of the Holevo measure, we can sort of go beyond it. And one of the things that we showed is that you can write something like a strong subadditivity in terms of conditional expectations and von Neumann subalgebras. And so if you recall the sort of classic strong subadditivity relation from quantum information theory, we can replace all of these traces or partial traces by conditional expectations. And this becomes a generalization, because what we're doing is we're taking a relation between entropies of distinct subsystems, and we're replacing that by a relation on subalgebras, which can apply to this case. But of course, there's nothing up here which says that this needs to actually apply to physically separated systems. You could, for example, again, have complementary bases of the same system or something in between. And so we can prove this essentially using the asymmetry measure formalism, but with adding and subtracting a lot of things together. And it sort of sets, I think, a new theme of this project, which is that we're looking at places where a trace can be replaced with the expectation over a subalgebra. So we also get this thing out, which is sort of like a halfway between a subadditivity and maybe something that kind of looks like a traditional uncertainty principle. And so this gave us some ideas about what we might want to look at next. And so after getting the strong subadditivity, which is sort of one way to go, comparing to a formula that is traditionally, again, defined on separated subsystems, we decided to go further with the uncertainty direction and look at what we can get that sort of has the form of a complementary basis relation. And so this is an uncertainty principle with subalgebras. We define this notation where we have a subalgebra conditioned on a subsystem as such, simply looking at, okay, what does the state look like after the conditional expectations and traces have been applied? And so in this form, we get something that is sort of in the theme of this Masson-Uffink uncertainty relation, but probably in other ways closer to the uncertainty problem, uncertainty in the presence of quantum memory, which is this paper by Berta and Christandel and several other authors as of 2010. And so this is interesting to us because, again, it's sort of taking something that looked like it was maybe more of a sub-corner of quantum information, which is this resource of theory of asymmetry, taking one of the measures out of that, looking deeper at what the implications of this were, and realizing it's actually going to touch a whole bunch of areas that are usually thought of as fundamental in quantum information. And so these are entropic uncertainty relations. And what I think is also interesting about this is that both uncertainty principles and these sort of SSA type inequalities appear to be sort of special cases of something you can do with conditional expectations on von Neumann algebras. And so in the traditional treatments of these, we would not necessarily think of these as being directly connected. But this is sort of saying these are sort of linked and they are related to each other. Now, there's this extra condition here, which is that we need to know something about the complementary channel of the conditional expectation onto one of these subalgebras in order to get this form, where we're looking at commutators of this subalgebra. And that's because the way that we derive this, unlike the previous two, where we had mostly applied what we knew about the Holevo asymmetry, we had to go back to the quantum channel formalism and essentially use the Stein-Spring dilation and the relations on entropies that come out of it to relate some of these quantities in the case where we have a good sort of knowledge of what the complementary channel looks like. And so we have the complementary channel to this coming out with that. That basically means that the environment ends up in this state. And so that allows us to make this step in these equalities of replacing the entropy of sort of the expectation onto this L prime subalgebra by the environment to a channel, and then looking at the Stein-Spring space of the channel, tracing out different pieces to relate that back to the original density and the original conditional expectation onto the subalgebra. And so that sort of gets us to a lemma, which again has asymmetry measures in it. Again, thinking of these less in terms of the resource theory of asymmetry than of the then as generalized conditional entropies in some sense. And then we need another lemma, which I think is somewhat similar to this SSA relation. It's again adding asymmetries and showing that you cannot get something negative. So this is sort of like the, this was going to be a finishing point of the talk, but since I promised to mention this, one other thing we did with asymmetry measures, for those of you who study index theory, which may not be the whole audience, you're possibly familiar with the Jones index and with this Pimsner Popa index approximation to it, or / other alternate index theory. And we showed that this Pimsner Popa index is actually related to the maximal asymmetry that one can create with a certain subalgebra. So taking the state that's maximally asymmetric, looking at the Holevo measure for that state, we get something that's equal to the index. So that was sort of interesting. Index theory is sort of very deep in, or at least thought of by physicists as something that is very deep within theoretical mathematics. But we may have sort of seen a glimpse of an interpretation of it. So that pretty much concludes. Again, this was a joint project with Li Gao and Marius Junge. I've also had a few conversations with one of Spekkens' students, David Schmid, who those have been very inspiring. And again, also thanks to the conference organizers and staff who allowed me to come here, and of course to the NSF several times over. And so in summary, we were looking at operator space tools for quantum capacity that also end up applying to resource theories of asymmetry. Along the way, we realized that these sort of lead to this notion of generalizing from a subsystem QIT setting to a subalgebra setting. And definitely the interesting aspects of commuting squares have become very apparent in this study. And so I'll leave this up here and take some questions.
Certainly it would be helpful to do the back and forth translations here, right? So these asymmetry measures have been proposed by other people also, or by Spekkens? Or
yeah, so
frames basically.
So Marvian and Spekkens proposed these, well, at least discussed these in one of their papers in, I guess, the earlier 2010s. So that was fairly recent. I think that several of these have actually been around for longer. So that was a paper that got a lot of attention. And then Marvian wrote a thesis on this topic, which has been very useful as a resource in that it goes into a lot of depth on sort of what different potential applications might be. And the reference frames are one of the, sort of, I guess, major points.
Okay. Yeah. Are there further questions? So let's thank our speaker and our speaker.